Hello and welcome to the AMIA Clinical Informatics Board Review course. This is Lecture 3B, Human-Computer Interaction, and I'm Bimal Desai, the Chief Health Informatics Officer at the Children's Hospital of Philadelphia. Here's the core content we're going to cover in this lecture. This is directly from the curriculum pages. Here it is in a little bit more detail. We're covering these topics on human factors engineering, which includes models, theories, and practices of human-computer interaction, human-computer interaction evaluation, usability testing, study design and methods, interface design standards and design principles, and usability engineering. Here's the key topics we're going to cover. And here is the sequence of topics that we'll do in this slide deck. So let's begin. First, by defining human-computer interaction. This is the field is defined as the study of people and computers, and it is a discipline that's very, very participatory. There's lots of disciplines that are involved in human-computer interaction. In that way, it's a little bit like informatics. This is a discipline that combines computer science, behavioral science, psychology, design, human factors analysis, and a lot more. Recently, there's been this recognition of its applicability to healthcare. Specifically, we know that HCI limitations are responsible for medication errors in many cases due to design that doesn't match the user's mental model, due to clunky visual standards, lack of standardization, and so on. We also know that this can ultimately lead to alert fatigue and cognitive overload, and it's been defined as one of the grand challenges facing clinical decision support. For example, we still don't know the best way to show a user a drug-drug interaction alert. I want to start with an example of why this is so vital to the field. And if you know or have read anything by Bob Wachter, you know that he's described in great detail a very specific medication error that took place at University of California, San Francisco a number of years ago. The blow-by-blow description of how this event took place in their electronic health record system was actually detailed in this long-form blog post called backchannel.com with an article titled "How Medical Tech Gave a Patient a Massive Overdose." And it's the story of a young boy who was ordered a catastrophically high dose of Bactrim, and the organization, University of California, UCSF, actually did a remarkable thing by being completely transparent about how this event took place and trying to deconstruct the steps that led to this error. And so I would encourage all of you to read this. I think it's really, really inspirational in terms of just how open and transparent they were with this very significant medication error. So the story was that this young boy was admitted to the hospital, the Children's Hospital, and was intended to be ordered for sulfamethoxazole trimethoprim that goes by the brand name Bactrim or Septra. And the initial intent was to order 5 milligrams per kilogram of Bactrim. And you can see here that the user had typed in 5, had correctly chosen the units of measure as milligrams per kilogram dosed in trimethoprim, and had used the accelerator button marked in blue to basically pre-fill that dose. And there's a set of calculations and a pale yellow warning at the bottom that I think are interesting. So one of the safeguards in this specific electronic health record is the ability to specify rounding rules. And in this case, because Bactrim comes in round tablets of 160 milligrams, you can't divide those doses, and so you can't divide them any smaller than a half tablet. So the organization set the rounding rule. This is the last line in that screenshot that says we are allowed to round this to the nearest half tablet. And this is sort of where the problem starts, that 5 milligrams per kilogram based on this child's weight would actually lead to a dose of 1.2 tablets, which you cannot administer. So the computer is trying to warn the user that, hey, look, you've asked me to round this to the nearest half tablet. I'm rounding it down to one whole tablet. And as a result, the dose that you're about to give this patient is 17% less than the dose that you want of 5 milligrams per kilogram. And that's what's in the yellow window. But that wasn't exactly what caused the error. So while one tablet would have been an appropriate dose, if very modestly underdosing, this hospital, like many hospitals, has a rule about, or a procedure rather, that if the physician's intent is to order a dose that is rounded by the computer by more than a certain percent, 10%, 15%, they have to go back in and explicitly enter that dose. In other words, the pharmacist is asking the prescriber to verify that it's okay to underdose his patient by 17% and give them just a single whole tablet of Bactrim in this case. So the pharmacist called the ordering prescriber and said, listen, this dose is rounded by more than whatever their threshold was. I need you to go back into the medication order and correct it so that you're ordering a round dose of 160 milligrams. So the ordering provider did that, went back to the order entry system, typed in 160, and hit submit. The problem was, and it's highlighted in red, that they did not correct the units of measure, and so the unit of measure here is still milligrams per kilogram. So the ordering prescriber thought they were ordering 160 milligrams, but instead ordered 160 milligrams per kilogram for a nearly 40 kilo child. This resulted in a prescribed dose of 6.2 grams of Bactrim, which would have been 38 and a half tablets. So a very, very large overdose, and you would think, well, it's such a comically large amount of this antibiotic that anyone could intercept this. But note that, first of all, it was easy to commit this mistake. And second of all, the system didn't stop the user from doing it. There was no max dose alert that says, wait, you probably don't want to give 38 and a half tablets of this medication. Numerous providers downstream in the medication administration process saw this, including the pharmacist. This is the screen that was shown to the pharmacist that says that the ordered dose of this medication was 160 milligrams per kilogram. And I would argue that if you take away the red boxes that I've superimposed on here, there's not a lot of guidance on this screen to actually tell the pharmacist that this is a catastrophically high dose. And I think there was probably some cognitive bias involved in saying, well, if the prescriber wanted to do it, or I remember just calling them and asking them to change it to 160 and ignoring the 160 mg per kg. Who knows in hindsight, and maybe it's detailed in the article, but for whatever reason, this escaped the attention of the pharmacist. It even got to the point where it was dispensed in individual tablet blister packs like this. So this is what 38 and a half tablets of Bactrim looks like. This was the dose that was actually sent to the patient's floor. And at this point, the reader is probably thinking, well, that's absurd. Who would give a patient this much Bactrim? And again, through a series of cognitive biases and deference to expertise or deference to the medical hierarchy, this dose was actually given to the patient by the nurse, tablet by tablet, leading to a very significant overdose of Bactrim. So that vignette of the young boy at UCSF who was the recipient of that massive overdose highlights just how critical it is for us to think about user-centric design in these electronic health record systems. And one model that I like is this one that's suggested by NIST that shows where in this process usability plays a role. So if you think about the various types of root causes for user errors, there's a number of them. Maybe you have the wrong patient record open, the wrong mode for an action, inaccurate data display, and so on. These are all human-computer interaction or usability-related errors that have been identified by NIST. And in and of themselves, they may not pose a huge risk to patients, but they are modulated by these other parameters. So you should recognize the four terms in the gray box there: severity, frequency, detectability, and we're adding one, complexity. Those four make up, they're very similar to the terms that we use to calculate the risk priority number when we were doing a failure modes and effects analysis. So it's basically saying that these are the things that can make a wrong patient record being open or inaccurate data display type of usability error into something much more significant, much more severe, much more common. And that those latent causes of error, because they're severe or frequent or not as detectable as they should be eventually lead to adverse events, which can lead to patient harm. So this is sort of the mental model for thinking about how human-computer interaction and usability vulnerabilities in a system can lead to patient harm. It also suggests that there's ways that we can evaluate the level of usability problems in a system by looking at workarounds and redundancies and user burnout and what they call low task completion rate. So this is the inability to complete a task correctly. You can see users sort of bail out on different activities. So now let's look at that top left box in more detail. Again, these are those different categories from that top left box. And all of us can probably think of examples of these kinds of errors from our own electronic health records. The first one that's listed here is the wrong patient usability error, where, for example, perhaps a user has more than one chart open and is working on the chart of patient A, gets distracted and is asked to do something on the chart of patient B, but doesn't click the toggle to go back and forth between the two charts and ends up entering the order on the wrong chart. The second one is when you have what's called the wrong mode for an action. And so using direct dosing, 100 milligrams, instead of weight-based dosing, 100 milligrams per kilogram, is an example of this kind of wrong mode for an action. And in fact, the error at UCSF was a wrong mode error. The third category is inaccurate data display, where perhaps because of the layout of the screen or the size or the width of the table that the data are formatted in, that a lab value gets truncated in a report. And this might cause the user to come to some incorrect conclusion because they're missing a vital piece of information. Another one is incomplete data display, where maybe a summary view only shows partial data. I've personally worked with and have seen systems where a summary view of vital signs only shows the last filed value for that time period, and which means that if you're looking at a collapsed view, you might actually miss the fact that there was an abnormal vital sign somewhere else in the time period. Another type of usability error are non-standard measurements, conventions, or terms. And we struggle with this a little bit in pediatrics because parents, of course, prefer English units of measure, such as pounds. And so we tend to use those more convenient units of measure in outpatient settings, especially when we're talking to families about how much their child has grown. But most of our weight-based medication calculations, actually, I would say all of them are done in metric units. So because we're asking users to switch back and forth between different standards of measurement or units of measure, it does increase our vulnerability to these kinds of errors due to non-standard terms. So for example, using pounds when you mean kilos, or kilos when you mean pounds, and either underdosing or overdosing the patient. Another type of error is the reliance or over-reliance on user recall. So for example, let's say that there's a screen where you expect the user to type in a number, but the number, like the verification of a lot number, is on a different screen entirely. And maybe this type of forcing of the user to use their own memory it will contribute to this type of nonsense data or incorrect data being typed in. Inadequate feedback is another type of usability error, and I think that you could make the argument that there was inadequate feedback about that rounding in the UCSF vignette, that it was, even though it was very clear in that last line of text that it was being rounded to the nearest half dose, perhaps it was less clear that as a result, the user needed to go back in and change it to 160 milligrams because the 17% rounding error or rounding was outside of the hospital's protocol. You could also imagine that maybe those rounding rules are configured incorrectly for your medication, and for something like an insulin dose where a tenth of a cc precision really matters, if you have a system that's silently rounding the dose to the nearest half cc, that's a problem. Corrupted data storage is the type of usability error where a user believes that a piece of data was entered or completed or submitted, but it actually was not. In other words, the data that the system receives are incomplete. So those were all examples of different types of human-computer interaction or usability errors. that can creep into these electronic health records. Now, if we switch gears and talk about different models of human-computer interaction, this is now into sort of the academic realm of how do you actually study human-computer interaction. And there are basically two categories of these models. There's what's called predictive models and what's called descriptive models. So we're going to start by going through some of these predictive models of human-computer interaction. And again, these are meant to they're meant to explain and in fact predict how a user might respond to a hypothetical system. The first one of these models that I want to cover is called the Hick-Hyman law. And this basically expresses the user response time as a function of the number of possible responses. And a simpler way of saying that is that the more options you have in for example, a hierarchical menu, like a pull-down menu or an unfamiliar list, it takes exponentially longer amounts of time to find the thing you're looking for. My favorite example of this is when you go to an online shopping site and you're being asked to choose your country at the end of the form where you submit, and you have to scroll all the way through literally a list of every single country in the world to find the United States. And then sometimes you find out that actually it was all the way at the top, listed under America instead. And it's a frustration, when you have to look through a giant list for a targeted piece of information, especially if that list is unsorted or sorted in some nonsensical way. Another model is what's called the keystroke level model, or the KLM. And this one actually sounds more complicated than it really is. It's basically saying that the total time to complete a task is the sum of all of the subcomponents of performing that task, which includes typing on the keys, pointing with your cursor, homing, which means dragging the cursor around on the screen, drawing, which means moving the cursor around with the mouse depressed, the mental operator or thinking, and system response operator, which is waiting for the system to do something. And if you looked at a certain process, like how long it takes to perform a certain function in your electronic health record, you might find that doing it the traditional way is actually very time consuming. And it's a good way to think about what are the types of functions, repetitive tasks that are most amenable to shortcuts or hotkeys. Where can you save the user time because they're performing these time-consuming tasks over and over again? Another predictive model is this one. It's called Fitts law, Fitts. And it basically says that the time that it takes to track an object with a cursor, to track to an object, or basically reach a target with a cursor, is a function of the distance you have to travel to get there and how wide the target is. So in other words, if you're trying to drag your mouse all the way across the computer screen to hit a target that's only 10 pixels wide, that's going to be very time consuming. It's going to be challenging to do, will require you to slow down and be much more precise towards the end, and perhaps either overshoot or have to change the mouse to get to where you're supposed to be. And they predict that the difficulty of this task, what's called the index of difficulty, or the ID, is equal to the base 2 logarithm of twice the distance divided by the width. And again, this should be fairly intuitive, that the longer that distance that you have to travel and the more narrow the target, the harder this task is going to be. Now let's go to the descriptive models. So these are ones that actually describe how a user interacts with a computer system. They're not trying to predict your performance with it. They're just saying this is how you can break down what the system does and doesn't do. And one of the more famous ones is this one called the Buxton three-state model of graphical input. And it's a fancy way of saying these are all the different things you can do with a mouse. It looks at all of the ways you can transition from dragging a mouse to clicking with the mouse to lifting the mouse off the mouse pad and so on. And so in this diagram, there's 3 states. There's out of range, which means that the mouse is off the table. Tracking, which means you're moving the cursor around on the table. And dragging, which means you're moving the cursor around the table with the button depressed. And notice that each one of these involves a transition state where you either raise the mouse or lower the mouse and depress the button or release the button. And you can imagine, I think the reason why I think this is applicable is that if you design a system in such a way that it basically requires or takes advantage of this specific type of graphical input device, that means that it's necessarily going to be more difficult to use with a different type of input device. And to me, this is the key reason why it's very challenging to use an application that's designed for keyboard and mouse on an iPad or on a tablet device. That if it's not custom purpose built from the ground up for a tablet, it's really frustrating to try to use an interface like that on a tablet device because this input model is so completely different. The act of typing on the keyboard, but specifically the act of using the mouse, is very different than tap, double tap, multi-touch, pinch to zoom, and so on and so forth. All the different models of how you interact with a tablet device. The next descriptive model is this one, Gaillard's model of bimanual skill. This basically posits that hands are not used equally, that because humans have a dominant hand, they tend to have distinct roles. And think about, for example, when you are drawing something on a piece of paper, you tend to brace the paper with your non-dominant hand and then use your dominant hand to actually write. So they have very, very different functions in that task of drawing something. It also explains why certain tasks are harder for left-handed providers, that the modern 101 key standard keyboard tends to cluster a lot of the function keys only on one side, which makes it challenging for users to use that. And then finally, this to some degree explains why certain pop-up screens, modal dialogues, might be ill-designed. If you think about it, a user of a mouse with their right hand, it's a very easy gesture for them to sort of flick their mouse down and to the right in order to reach a button, for example, on the bottom right of a screen to acknowledge or dismiss a pop-up dialog. It's a little bit trickier, maybe not a lot, but it's a little bit trickier for a left-handed person to do the same thing. It's not as natural a movement, and actually hitting the corners of a box are a little bit easier than hitting something that's free-floating. So it's that kind of acknowledgement of handedness and how it either serves us or hinders us when we're using an interface. That's what's being addressed by this model of bimanual skill. Next, let's talk about usability evaluation. There are three main categories of usability evaluation. There's testing, inspection, and inquiry. And within the testing category, there's a couple of techniques that we're going to cover. One's called coaching, one's called thinking aloud, one's eye tracking or click tracking, and one is actually directly measuring the user's performance. There's two techniques for usability inspection that we're going to cover. One's called the cognitive walkthrough, and the other one's called the heuristic evaluation. And then there's the third category of inquiry, user inquiry. This is where you're actually talking to users or observing them in the field with focus groups, surveys, looking at usage logs, and you're seeing how the system has been used in real life. So the usability testing techniques, what they all have in common is that you're asking a user to try to perform a task, typically in a simulated system. This is not the real thing, and you're taking exhaustive notes about how they either achieve the tasks or fail to achieve the tasks, what worked well, what did not work well, and so on. In the first one, the coaching method, the user is asked to perform a task, and they're allowed to ask any questions that they want to an expert coach who's sitting right next to them. And the expert coach is allowed to answer the questions, but they're also keeping track of all these questions because they might realize that something that the designers thought was completely intuitive is very, very frustrating or counterintuitive to a large group of users. They might also identify that there are some things that they can't simplify in the user interface, but which are persistent points of confusion, and therefore they need to make sure they address them in their training and documentation. The second style of usability testing is thinking aloud. This is where a user would attempt to complete a task and basically narrates the entire process as they're doing it. Okay, now I'm going to open this screen. I'm going to type in this medication order. I'm going to type in this dose. Oh, I think I see an error. Maybe I need to read this in more detail. Okay, I'm going to correct the dose and then go to this screen, and so on and so forth. They basically articulate their difficulties, their confusion, any aha moments they've had about the interface. Maybe the coach is actually keeping track of the fact that they did or did not see certain shortcuts and accelerators, or did or did not use them. And again, like the coaching method, this is one where if you have somebody think aloud, you can pinpoint exactly where the user interface has led them astray. This one is a little bit more advanced, the eye tracking or click tracking. I know of a couple of health systems who have usability labs that do this kind of thing, but basically there are now camera apparatuses or little rigs you can have the users wear such that you can see where they're paying attention with their eyes, or you can see where their mouse is traveling. And it's a good way of saying is the information, or it's a good way of finding out whether the information hierarchy on the screen is appropriate. Maybe the most important thing on the screen should not be in the bottom right of the page because that's not where the user tends to track. And so this kind of tracking software, I think, are becoming more readily available. I'll tell you that I don't think health systems often do this kind of work. This tends to be the work that, for example, EHR developers hopefully are doing in some of their usability labs, or even HCI researchers themselves. The next category is performance measurement. Ideally, what you would do is you'd assemble a group of about 5 to 8 users, and you would have them attempt to complete a set of specified tasks. And then as you're watching them as the evaluator, you're keeping track of how long it takes them to complete the task, how often they actually complete it versus how often do they bail on the task. You're looking at something called the recovery rate, which is if they start down the wrong path, they start to almost commit a dosing error, but then they recover. How often does that happen, that they make a misstep but then recover? You're looking at the failure rate itself, where they're simply unable to complete the task. You're looking for frequently and never used features. So maybe the designers intended a very specific workflow and the users just ignore it entirely because they found another way to do it. And you're looking for tasks that have multiple ways of accomplishing the same thing, measuring which ones the users prefer and how they choose to do it. So this next category of usability evaluation techniques is usability inspection. And the first one we'll cover is cognitive walkthrough. Typically in the cognitive walkthrough approach, what you're looking at, what you're showing the user is a simplified representation of the interface, or an incomplete or a mock-up version. These can be what's called a low-fidelity prototype or a wireframe prototype, where it sort of blocks out where the key functions are going to be. And what you're trying to find out is whether the user will try to achieve the right effect. So, for example, will the user know, based on the instructions you've given them, that the system requires a weight? Will they know that they're supposed to enter a weight and where and how they're supposed to do it? Will the user notice that the correct action is available? Will they see that there's a button that they're supposed to press? And will it be completely obvious to them what they're supposed to do to complete the task? Will the user associate the correct action with the effect that's to be achieved? In other words, are the labels intuitive and easy to follow? And then finally, if the correct action is performed, will the user see that progress is being made towards a solution of the task? So does the system provide them adequate feedback? For example, if they're in a multi-step process like medication reconciliation, is it completely clear to the user that there are only 2 out of 5 steps into it, or something like that? Next is what's called a heuristic evaluation. And remember, we said that a heuristic was sort of a shortcut. And in the same way, when you're doing usability testing, a heuristic here means a sort of a general design principle or a rule of thumb. Probably one of the most well-known rules of thumb or heuristic checklists for web design was published by this investigator, Jacob Nielsen. And you can find this on his website, useit.com. Nielsen described these 10 usability heuristics, many of which are completely relevant to the design of electronic health records. And these are things that you would think in this day and age are completely intuitive and every web developer or designer or software designer would follow. But none of us would be shocked to find that many of these things are ignored. So these are the 10 Nielsen principles of user interface design. And the reason why this is listed as a heuristic checklist is that you can look at an interface, at a software interface or a web page, and you can say, how many of these principles does this interface violate? And basically, without formally testing it with users trying to do task completion and that kind of stuff, you can critique it using these shortcut or rules of thumb. So, for example, the system status should always be visible. It should be clear if you go to a shopping website, my favorite example, and you make a purchase and you hit submit. Can you be certain that it's not going to accidentally resubmit your credit card information if you keep clicking submit? You want to make sure the system should tell you, okay, I'm processing this credit card transaction. It might take a second, so don't hit submit again. Otherwise, you might get double billed. The second one is there should be a match between the terminology and the concepts used by the system and those that are in common use in the real world. This basically is an argument for synonymy and making sure that the way that you refer to terms in your electronic health record or in your computer system match what the user expects to call it. The third one is that the system should give users control and the freedom to undo, redo, or exit a task. And if you venture down a workflow that looks like they can't back out, then that's extremely frustrating from a usability standpoint. Next, the system should be consistent and use standards where possible. We're all in favor of standards. Next is that a built-in error prevention strategy is better than a clever error message. And this is one of those key mantras of decision support, which is that if we can guide the user to do the right thing, we hopefully won't have to show them a pop-up alert later. Number 6 says that a user's recognition of icons and pathways is stronger than their recall. By showing options that facilitate user action, one can avoid forcing users to memorize sequences of menus or keystrokes. So in other words, make it easy for them to recognize what the function of a screen is, and make sure you're making it easy for them to understand what they're supposed to do next and in what sequence. Number 7, the system should support novice and expert users with shortcuts and accelerators. It would be great, especially for very stereotyped and repetitive tasks in the EHR, to have kind of shortcut ways to do that. Number 8, dialogues should be sparingly written and the design should be minimalist. And there actually is literature in the informatics world to back this up. I know that an investigator named Jan Horsky has done some work to show that very lengthy pop-up dialogues are often ignored. And if you really want to use it to pay attention to a decision support rule, you should make the alert text and the recommendations short and sweet. Number 9, the system should help users to recognize, diagnose, and recover from errors. And number 10, the system should provide succinct and context-sensitive help and documentation. So, these heuristics are designed for websites. There are increasingly heuristics for things like the design of interruptive alerts in the in a clinical decision support system. There are recommendations from different organizations on how to design order sets. For example, we use a set of checklists or a set of heuristic techniques when we're scrutinizing new submissions for order sets within our institution. So that's an example of doing a heuristic evaluation, even though it's not formal usability testing with a group of potential users. Next, there's usability inquiry, and this is again where you're asking users of the system how they found the experience of using it, whether it's through surveys or focus groups or direct observation. You can also go back and look at usage logs to see in real life how is the system being used or not used. So Jacob Nielsen also described this strategy called discount usability engineering, and the discount here refers to the fact that you could do it sort of on the cheap. It's a method of evaluation that was intended not to require a large number of people or a large budget. Nielsen recommends that you start with about 5 testers and you perform a modified version of both usability testing and usability inspection. So this would include a modified think aloud, a heuristic evaluation, and then a low fidelity prototype to test one process at a time and then to rapidly iterate. So you show them a mock-up, you get their reactions to it as they try to use it, and then you can redo it. And the beauty of these low fidelity prototypes, as we'll talk about in the next couple of slides, is that they actually don't have to be that complicated to make. These days, I've seen people use a bunch of online tools for designing what look for all the world like real user interfaces, but are actually low fidelity prototypes. There's no coding behind them. It's just boxes that look like buttons and parts of a screen. I've seen people who can mock these things up actually in PowerPoint or other your favorite slideshow application, to the point where they can animate keystrokes, and so you can make it appear to the user that they click a button, some action takes place, some window pops open, and so on and so forth. So again, you can get really creative with creating these prototypes and not do a lick of coding to create the actual user interface. More about these wireframes or lo-fi prototypes. Again, the intent here is that you want to gather as much feedback as you can without actually investing the time, energy, and money and resources in building the interface. And this is a smart way of thinking about it, because as we know from software development lifecycle and software engineering, it's way cheaper to identify usability errors early on before you've coded a whole lot of stuff and built a system around it than it is to do it later on after the system's sort of more set in stone. As I mentioned, these can be paper-based. They can be full. They can mimic full applications. These are a couple of websites, proto.io and atomic.io, that allow you to basically create what look like computer interfaces with drag and drop software. And you can also do wireframes. And wireframes are basically where you block out, using boxes with X through them, the general space and the general layout of a website. People have proposed that there are advantages to showing somebody an intentionally low fidelity prototype. In other words, even though these days we can make a high fidelity prototype using some of these tools that are listed here, one that looks and feels just like a real software interface, even though it's not, there may be some advantages to keeping it low fidelity. And the argument is that if the interface looks less polished, if it looks less finished, you're rendering the colors in grayscale, so it looks like it was drawn by hand. You use sort of a fat magic marker effect when you're drawing the boxes out, so it looks like it was sketched out. In the mind of the person who's testing the interface, it feels like it's more fluid. And the converse is that if it looks like it's completely finished or it's already been developed, they're less likely to give you constructive feedback, because they feel like, well, this interface is completely done. I don't really have an opportunity to change it at this point. So that's the argument for perhaps keeping these things low fidelity. Thinking more about low-fi versus hi-fi prototypes, the low fidelity ones are cheap. Theoretically, they're supposed to be quicker, but as I mentioned, the software tools these days often allow you to toggle back and forth between things that look intentionally low fidelity and things that are intentionally high fidelity, so they look like the real thing. The other advantage is they allow you to quickly visualize different designs. Maybe you can mock up 5 or 6 versions of the same page without, again, having to code anything. And the high fidelity prototypes, these can look as good as the actual finished user interface, and they might allow for more accurate testing of things like task completion, because again, the user doesn't feel like they're banging on a piece of paper. They actually think that they're clicking on a real software interface. So here's an example of a low fidelity prototype, actually a series of prototypes going from the paper sort of wireframe to something that looks a little bit more realistic, to something that adds color and starts to block out space and propose navigation, all the way to something that looks almost finished. Now this is from the usability.gov website. What I think is particularly clever is the way that they took the face of an old smartphone, just the glass face, and in order to simulate what it's like to scroll through this website, you basically slide the piece of paper up and down behind the glass. I just thought that was really clever. As I mentioned before, a wireframe is a type of prototype that's used to suggest the basic structure of a user interface and the relationship between pages. It's often the beginning point, the sort of blueprint for the design, and that software developers can use these to kind of rapidly mock up what the sites are supposed to look like and how they relate to one another. This is an example of a low fidelity prototype that I built once some time ago. I was trying to show what a Bayesian calculator might look like on a smartphone. And I built this in one of those software applications. I think this was from Balsamiq. And I clicked a button to make it intentionally look low fidelity. So if you look at like the home button on this smartphone interface, it looks like it was done with a chunky black marker, and that's completely on purpose. When you want something to look lo-fi, the intent is to give the user permission to modify it or to critique it. The other feature of this was that I could hook up different actions to different buttons. So you notice that one of the buttons on this interface is blue. If the user clicks on that, it actually automatically switches to the next screen to emulate what would happen if they clicked that in the real application. So the argument often for us is that, well, we don't really control the usability of our systems. We don't really have the opportunity to do much prototyping with commercial electronic health records. And in that sense, the experience of use for commercial EHRs is often less flexible. But I would challenge that a little bit, that we do have some opportunity to prototype with commercial electronic health records. And one of the examples is actually from Dr. Lee Milligan, who was a former attendee of the CBRIC course a couple of years ago and was very gracious to share this mock-up with us. So Lee was working at his healthcare system and wanted to accelerate the process of developing a specific report in his electronic health record without having to spend the development time to do it and then to possibly tear it down and edit it and revise it and so on and so forth. So he started, like all good UX designers do, and UX, by the way, stands for user experience, first with a prototype. This is Lee's low-fidelity paper prototype for what he was calling the iCode report. This was supposed to be a one-page report you could generate quickly in the electronic health record that would give you all the relevant vital signs and lab tests that you needed during a critical event like a code event. And you can see how he just sort of blocked out. You could say that this was something like a wireframe where he generally just blocked out the space on the page and indicated where certain things went, like the current meds. Slightly more refined than that, Lee did a slightly higher fidelity prototype in, I think this was in Word or Excel. And you can see now this is starting to look like the real thing. It even has the recent rhythm strip down on the bottom right. And then finally, the finished version in his electronic health record, which I've blurred out. But the name is now changed. It's not called iCode anymore. It's called the Code Runner. But the general layout of this report is exactly what was defined in those paper prototypes. It's just that getting user agreement about the layout, the sequence, and such was probably easier and quicker to do on paper than to build it in the electronic health record and then risk having to go back and change it. I think one of the really nice trends in the past couple of years has been that we've seen the increasing importance of design standards to our field. Until I think fairly recently, there were not really widely accepted standards for user interface design, and we didn't really perhaps pay as much attention to human-computer interaction in healthcare as we should have. But you can see from the list here, it's been an area of active innovation and research. Again, many of these by these investigators, Jan Horsky, Blackford Middleton, and all of their colleagues. And so this first citation is the design of decision support interventions for medication prescribing. So these are general recommendations for how to think about decision support for medications. The second one is interface design principles for usable decision support, a targeted review of best practices for clinical prescribing interventions. And the third one is enhancing patient safety and quality of care by improving the usability of electronic health record systems, recommendations from AMIA. All three of these are actually worth a read because they sort of give you some insight into where the field is going and the type of research that's being done in this area. I still go back to this notion, or unfortunately this limitation, that we probably don't have the same degree of control as we did when these were homegrown systems. Now that we have commercial electronic health records, much of that design and interface is set by the vendor themselves. On the flip side, I'll tell you that these vendors have far more resources than health systems probably did to actually do the formal usability testing. And I've spoken with representatives from some of these major vendors who have reassured me that they have they actually have a decent amount of testing staff who can help them do usability testing, and they do test it in the field as well. So I think there's light at the end of the tunnel, and hopefully in our lifetime we'll see that the attention to human-computer interaction will only increase for commercial electronic health records. So looking at all of this, what of these lessons can we apply to electronic health records? What can we take away from all this literature? And the best summary I could find was this NIST publication from 2012 that recommended a sort of standard for testing and validation of EHR usability. They proposed this 3-step approach that includes a lot of the techniques that we've covered previously. So step 1, they recommend you do an EHR application analysis. So this is the sort of workflow diagramming and things like that. Who are the users? What is their work environment? What tasks are they trying to complete, and what do they do? What should the interface look like, or what does it look like? What mistakes might they make because of the design of the system? Really sort of scrutinizing the environment of use for this application. And what evaluation has been done to mitigate the mistake and improve usability. Step 2 is to do an EHR user interface expert review. And notice that they recommend, like Nielsen, a 2-person heuristic review. Go through a checklist of sort of best practices that your organization has come up with, or use one of the existing sets of best practices, or the recommendations from organizations like Leapfrog or whoever, and actually scrutinize your user interface design. Also, confer with clinical subject matter experts to look for potential sources of errors. And this one's actually very, very useful. This is, again, I think step 2 is closest to what our Clinical Decision Support Committee does, where we do a heuristic review of all order sets. And we basically have a room full of people who are clinical subject matter experts, ordering providers, pharmacists, nurses, inpatient and outpatient folks. And they're looking at this from the viewpoint of, okay, if I were to use this system, where would I be confused by this as a naive user? And then step 3 is the formal testing, the user interface validation testing. And this is where you do direct measurement of performance, looking at task completion and other associated metrics, and maybe even then interview some users afterwards, doing some post-testing interview. All 3 of these things together, you can probably do, especially step 2, without breaking the bank, without putting in a whole lot of time, energy, and resources. And so I think this is actually sort of a very rational recommendation if you're trying to design a new set of screens in your electronic health record about how to approach this. This field has gotten so much attention that it's actually sort of blossomed in its own area of informatics called cognitive informatics. It's the study of how humans process information and how and why we make decisions when we're confronted with certain types of interfaces. One of the leading areas in this, leading institutions in this area of investigation is the National Center for Cognitive Informatics and Decision Making in Healthcare, located at the University of Texas Health Science Center in Houston, along with 9 partner sites. They are one of the recipients of this Strategic Health IT Advanced Research Project Award, the Sharp-C Award, and it's led by Dr. Jiaji Zhang. Within Sharp-C, there are 5 sub-projects. The first one's listed here is Project 1, the Work-Centered Design of Care Process Improvements in HIT, looking at EHR usability and workflow. Project 2 has 2 sub-projects, Cognitive Foundations for Decision-Making, Implications for Decision Support, and Part B, the Modeling of Setting-Specific Factors to Enhance CDS Adaptation. Project 3 is Automated Model-Based Clinical Summarization of Key Patient Data. Project 4 is Cognitive Information Design and Visualization, Enhancing Accessibility and Understanding of Patient Data. I think one of those projects, either 1 or 2, gets counted as 2 separate projects, which is why there's 5 projects total, but only 4 bullet points on my slide. One of the resources that's available to all of us for free as a part of this Center on Cognitive Informatics is this textbook called the Better EHR book. You can download it for free. It's a free PDF or an iBook, and the link is here on the bottom right. They describe a tool that was developed as part of the Sharp-C project called the TURF EHR Usability Framework. TURF is an acronym that stands for Task, User, Representation, and Function. And it's basically a way that you can look at a user interface, take notes on it, scrutinize it, and characterize the usability defects in it. You want to basically critique the interface on some of these main dimensions. Is it useful? Is it usable? And is it satisfying? Meaning, does it give you a good subjective experience? And this is what the Turf usability software looks like. You download it. You basically upload into the Turf framework your screenshot of your application. And here is where you mark it up. So you can see that maybe it's not so hard, not so easy to see. But in the middle, the user has, in a red rectangle, highlighted a specific part of the medication list interface. It looks like it's a search feature of some kind. And now they're basically saying, okay, all the notes about usability that are on this screen relate to this specific feature or this specific part of the interface. It's also a tool that can allow you to capture usability survey data from directly from end users. Another very, very practical output of this work are these safety-enhanced design briefs. These are guidelines that are meant to coach anyone who's trying to design their own system or improve their own system in a number of different EHR use cases. So, for example, it'll go through and tell you what are the effective uses of color in a user interface. Why is it that you can't just make everything bold red, for example? There's another guideline on the correct way to design a table for optimum visibility, viewability, legibility, decreased eye fatigue, and so on. Another one for reducing wrong patient selection errors. There's recommendations for how to do that. How the preferred ways to display and allow users to manage results. The best ways to show drug and drug allergy checking alerts. How to format and display the medication and allergy lists. Decision support rules, e-prescribing, and so on and so forth. Each one of these is maybe 1 or 2 pages long. They're high impact. They're actionable. They're evidence-based. These are a great resource, and I highly recommend that you all take a look at. Here's an example of the design brief for how to use color. And you can see that they actually show you real or mocked up interfaces, and they suggest both good and I think in some examples, bad examples of the use of color. So the first principle here for use of color is to maximize the communication benefits of color and design. Use grayscale where you can, and then add back color in a very sparing way. Use black to represent information that actually matters. Use gray to show information that can fade into the background. You don't necessarily immediately want to call that to the user's attention, but you want it there if you need it, like timestamps and things like that. And then in this case, you notice that the abnormal lab data are highlighted in this sort of pale orange. The second principle here is something like to group items into different categories. Use no more than 7 colors and preferably no more than 4 colors. So if you're doing a bar graph or a histogram of some kind, don't have more than 4 to 7 different categories because they become illegible. I like this next one too, that to show sequential ranges of quantitative values, use 1 color if the data are sequential, 1 color scale, and use a diverging or 2 color scale if you're looking for to show a range of values that go from one extreme to another. This is the design brief for reducing wrong patient errors, and it does give some evidence-based recommendations for things like to help remember patients, identify and to locate them in the list. Don't truncate their full names. In addition to their names, consider adding their photos and other identifiers such as dates of birth, main complaint, or chief complaint or diagnosis. Here's the one on decision support, and it has some fairly useful things about how to create consistent, useful, reliable alerts, how to prevent alert fatigue, and things like that. Sort of an offshoot project of the Sharp-C project is this one called Inspired EHRs. This one is not a recommendation or a set of heuristics, but it's meant to be more aspirational and provocative. So it says, imagine if you had the ideal electronic health record and you could design it from scratch, what would it look like? So these were not formally tested, but they were reviewed by experts. And some of them I think are really nice because it shows you how much of an impact visual appeal and aesthetics has on. And here's an example of some of those principles being used. So on the left, you can see what looks like a medication list, and this could honestly be any generic medication list in any generic electronic health record. There's no specific formatting other than the fact that they list each medication as an indented list. But nothing in here really jumps out or calls to your attention the most important information, and there's no sort of visual hierarchy of this information. Whereas on the right side, they've done a few clever things. First is they've told you this is a medication list. They've given you in gray the information that was updated a month ago. Now the names take the prominent position. You don't even have to indent them, but if you bold them and make them a slightly darker contrasting color to the rest of the list, the user can easily visually identify the list of medications. And then the next most prominent thing on the list are the doses, and the concentrations and dose forms. And then the next most prominent thing are the actual signature, the once or twice daily, the frequency and the interval and the route and all that. Here's another one that shows the influence of good formatting on the design of tables. Again, the left one could be any table that any of us have either put into an Excel spreadsheet and shown to a user. And the right one is this sort of cleaner version of it. The visual argument here is that those dark black lines on the left, they offer no information. And in fact, all they do is they sort of entangle your eyes and distract them from the actual information, which is the list of medications. So the recommendation here is to just get rid of those black lines and to, again, decontrast or to fade the contrast of almost everything except for the most important information. So the headers, the alternating rows, the second column entirely goes to these sorts of shades of gray, and it's only the names of the medication that have the darkest color and the highest contrast with the background. Again, using a really subtle application of color and visual representation to highlight the importance of specific information on the page. One of the leading proponents of this manner of thinking, of how you display visual information, is Edward Tufte. And this visual display of data, there's almost like a whole track of talks and discussions on this at AMIA each year at the national conference. And it's a topic that's mentioned throughout the Sharp C work, and it is, I think, very, very important to our field, specifically because we know that when we get this wrong, the results can be catastrophic. And Edward Tufte made the argument that these can have really, really serious consequences if you do it incorrectly. If you don't know how to convey visual information, if you don't know how to make an argument through pictures and diagrams and charts and graphs, then you're underselling the evidence, and moreover, you're probably putting people at risk. And the example he gives is the Space Shuttle Challenger disaster. So you remember that back in the 80s, Morton Thiokol was the manufacturer that was in charge of building the subcontractor who made the O-rings between the segments of the rocket boosters on the Space Shuttle Challenger. And these O-rings actually had sort of a sordid history of failure, and they knew that under certain conditions these O-rings would fail, sometimes in catastrophic ways, causing the rockets to explode or to malfunction. And somehow Tufte dug up some of the original slides, the mimeographed slides that were used when the engineers were trying to show the project team that there was this risk of failure. And this was the graph that he pointed to, or the diagram he pointed to, showing, 9 rockets with temperature markings and different color-coded or hatch mark-coded indicators for how and when these things would fail. There's no specific point to this. In other words, if you look at this, you cannot at a glance see if there's a pattern or a relationship. And he argues that this specific choice of representation completely obfuscates the relationship between temperature and O-ring failure, and that actually was one of the root causes of the Space Shuttle Challenger disaster. So he takes his hand to this graph and sees if he can redesign it a little bit. The first thing that Tufte does is he introduces an x-axis, so it's easy to see that as you go up, there's increasing temperatures. As you go to the left, there's decreasing temperatures. And then he stacks the data in these sorts of almost like a histogram or a bar plot, showing you at what temperatures they had the most failures. And he critiques his own design and says the problem is that the pictures of the rockets don't offer any additional information. So let's get rid of the rockets, because we don't really care about the pictures of the rockets. What we do care about is the severity of the failure. Were these like trivial failures or like very, very major malfunctions of the O-rings? And so he reformats it one more time. But before I go to the next picture, I want to show you that he also shows you on the very, very far left that on the day of the launch, it was 29 degrees. And that was a temperature they'd never tested anything at. So there's this lone rocket way out to the left representing a range of temperatures that were never actually tested by the engineers. And this is sort of his final version, where now he's gotten rid of the rockets. He's added on the y-axis not just the number of rockets, but actually the severity of the O-ring damage. And you can see now that there's this clear upward trend that as temperatures decrease, the severity of O-ring failure increases almost exponentially. And this tells a very different picture than that first graph. In fact, it suggests that it was almost unavoidable that on the day of the launch, when the temperatures were between 26 and 29 degrees, that they would see some form of O-ring failure. So again, simply thinking about how you display the data can completely change how the viewer receives the information and assimilates that information. And think about how this might apply to the display of lab results or to the display of other types of patient data. Well, Tufte did exactly that. There was this publication in '94 in The Lancet where Tufte actually tried to apply some of his design principles to the sort of if we were to design the ideal visual display of lab records. I think he maybe have been on the right track, but I'm not a huge fan, honestly, of these small multiples, these box plots. I think what's missing here, and you can't really fault Tufte for this, is that he doesn't have perhaps the clinical background to put these into any sort of logical grouping. So I'm not sure why temperature is listed next to the haloperidol dose, is listed next to insulin, and so on. And so it's not for lack of trying. Maybe this misses the mark a little bit, but it's great for people in our field to think creatively about how we want to visually display data. And I think it'll be an exciting area of research in the years to come. So that's the end of this lecture, and thank you very much. There are some other additional readings for anyone that's interested. I've got links here to the backchannel.com blog post, to the Better EHR resource, Inspired EHR, both of the Nielsen websites, many of these other NIST standards, and things like that. For additional self-directed learning, there is a curriculum on usability.gov. That's a very good resource. And for the board review, consider looking more at usability evaluation, looking more at wireframing and prototyping. These are all modules that are in that usability curriculum. Also, if you want to learn more about paper prototyping, you can go back to Jacob Nielsen's website, the nngroup.com website, links listed here. Thanks a lot.